California's greatest cities and millions of her citizens live in constant peril. Since records began, there have been 13 large earthquakes along the San Andreas fault.
The water lines have ruptured. There is no water coming out of the fire hydrants.
And now, America's geologists, her rock detectives, are warning of a potential disaster.
The major damage has been done.
In the fall of 2008, more than 300 scientists calculated what a major earthquake would do to Southern California.
We've been conducting a special study of a magnitude 7.8 earthquake on the southern San Andreas fault, large enough to potentially damage tall buildings. Fire will be very significant.
The definitive scientific report presented to politicians was codenamed Shakeout. It forecast thousands of deaths and billions of dollars of damage in the city of Los Angeles, which makes it crucial to investigate the most important question: when will the next big earthquake hit the San Andreas fault? The latest preparations for disaster are the climax of an investigation that started more than 100 years ago. In the aftermath of the Great San Francisco earthquake of 1906. The earthquake struck on a Wednesday, just before dawn. The ground shook violently for 45 seconds, igniting fires that raged unchecked for the next 4 days. "28,000 buildings, a tenth of the entire city, were destroyed, and more than 3,000 people, 1 in every 100 of the population, were killed. With a magnitude of 7.8, it's in the top 20 of North America's strongest ever earthquakes. The scale of the Great San Francisco earthquake shocked the nation. But no one understood what had made the city shake. Native American myths explained earthquakes as shocks from a battle between warring spirits. Latter-day explorers couldn't understand the shocks that destroyed their mission buildings. One Spanish missionary wrote, "The earth shook around me from explosions under the ground." 300 years later, and science has still made little progress. Refugees in the ruins of San Francisco still blamed earthquakes on mysterious underground explosions. So, just 3 days after the earthquake, the state of California asked one of the world's most famous geologists, Andrew Lawson from California State University, to investigate what had destroyed the city. He and a team of 25 scientists began collecting damage evidence in the city and surrounding countryside. There were roads that had buckled, rail tracks that had twisted. The most startling evidence of all? That came near the town of Bolinas in Marin County, to the north of San Francisco. This picket fence had an 8-foot gap in the middle. Before the earthquake, it was a solid boundary fence dividing 2 fields. But when he recreated what had happened, Lawson realized that the land had jolted apart and torn the fence in 2. Plotting the evidence on a map around San Francisco revealed a surprising pattern. Because connecting the dots drew a straight line. And at every point, the earth moved in the same way, on the coast to the north, inland to the south. This line of weakness was the culprit they were searching for. South of San Francisco, the suspect line ran underneath a lake, the Laguna de San Andreas. So now, the earthquake perpetrator at last had a name. Professor Lawson, who a decade earlier had identified cracks in the earth here as a harmless rift, now rechristened it the the San Andreas Fault. In modern-day San Francisco, the buildings, the roads, and the railways have long since been repaired. But if you know where to look, evidence of the 1906 quake can still be found. Geologist Charlie Paul follows in the footsteps of Lawson's team, seeking signs of the havoc from 1906. He finds it on the cliffs at Muscle Rock, 12 miles south of San Francisco.
The cliff is not here by accident. There's a very good reason why this cliff is here. Half a mile or so of the shore face apparently fell off in the 1906 earthquake. And if you look down below us, there's a big rotated block that's near the present-day shoreline. And it is just inboard of the San Andreas Fault. The San Andreas Fault is about a quarter of a mile offshore here. And of course, that's one of the major crustal junctions on this side of North America.
Modern computers can now trace how damage waves spread out across the city, and that pinpoints where the quake originated along the San Andreas. It was offshore, about 2 miles out to sea from the Golden Gate Bridge. So, to continue tracking the fault, the investigation must head out to sea. Marine geologists use remote operating vehicles, mini submarines, to map the seafloor.
What you'd see is subtle variations in the topography, or topography that would not naturally line up. So there might be a line on the ocean floor that is higher or lower on one side, and you can use various techniques to determine that this actually is a fault instead of some other process.
Running south across the seabed, the San Andreas finally runs out of ocean and hits the land. This broken line of rocks, stretching in from the sea, marks where the San Andreas hits land 12 miles south of San Francisco.
We're here at Muscle Rock, and we're essentially standing on the San Andreas Fault right now. And if there was an earthquake, I don't know what would happen right here, but I wouldn't want to be here.
This Pacific coastline, where cliffs crumble slowly into the sea, is the boundary between two of the Earth's massive continental plates. Separated by the San Andreas Fault, two vast separate blocks of the Earth's crust lie directly alongside each other. Here, the continent of North America lies slightly on top of the adjacent section of crust which holds the Pacific Ocean. The join can be seen where these lower, darker rocks are overlaid by light-colored sedimentary rocks.
These rock types differ by more than 100 million years in age. Two rock bodies that are not similar in any way have been brought together.
The fault line was exposed to geologists when the cliffs collapsed here in the 1906 earthquake. But back then, nobody understood how and why the two different types of rock were next to each other. Until around 40 years ago, when the answer was finally revealed by the theory of plate tectonics. The theory showed that the Earth's crust consists of separate moving plates on which the oceans and continents sit. Around 200 million years ago, the heavy Pacific Ocean plate collided with North America and started sinking underneath the lighter continent. Professor of Geophysics Mark Zoback studies that process, called subduction, in his laboratory at Stanford University.
For many millions of years prior to the existence of the San Andreas Fault, the Pacific plate was subducting beneath North America. The oceanic plate was diving down, and that process went on for, well over 100 million years. So a tremendous amount of activity was occurring.
As the unstoppable force of one plate met the immovable object of the other, they were forced to change direction.
About 20 million years ago, the plate motions were such that the Pacific plate had to start sliding north with respect to North America. And now, the principal motion is this sliding process between the two plates. And 20 million years ago, the San Andreas Fault was born.
It was the moving plates that crushed different types of rock together, just as here at Muscle Rock. At last, the investigation knows what it is dealing with. The San Andreas Fault is 800 miles long, emerging from the seabed north of Point Arena in Northern California and running down to the Salton Sea in the south. The evidence is coming together. Clues from the 1906 earthquake, such as the picket fence that was torn apart, prove that the land was moving. Connecting the dots identifies the straight line of the San Andreas Fault. And Muscle Rock uncovers different plates of the Earth's crust on either side of the fault line. But investigators still need more information about how often the San Andreas has spawned earthquakes in the past. It might help them answer the all-important question: when will the San Andreas strike again? To discover when the San Andreas Fault will strike again, the investigation needs to know about ancient earthquakes that have struck along the fault line. But there's an immediate problem.
So here in California, it's a particular challenge, and some of the earliest written records were from the missions and from the early explorers, so only dating back into the 18th century here. Other parts of the world, we have an earthquake history going back millennia.
The investigation moves 350 miles south of San Francisco to a desert where the San Andreas may have been active for thousands of years. There's crucial evidence here about earthquakes from ancient times.
This creek used to flow straight across the San Andreas Fault here, but several earthquakes formed a natural dam where the San Andreas Fault wedges up here in front of me. That created a small pond, and now we're looking at the dry sediments of that pond that record the history of earthquakes, and that tells us quite a great deal about the past behavior of the San Andreas Fault.
Some of the clues are so small that Hudnut's detective work gets him down and dusty among tiny cracks inside the fault.
Sometimes we can find out about the past behavior of the San Andreas Fault by looking at the tiniest details.
At the bottom of this small ancient pond, mud sediments collected above a fine line of pebbles. Then, an earthquake shifted the land upwards on one side of the vertical fault line.
So this layer was originally flat, and then, in a subsequent earthquake, it was broken like this along this tiny fracture strand of the San Andreas Fault.
But finding proof that this is the site of an ancient earthquake is only part of the story. Hudnut needs to know how long ago it happened. The bare rock layers are no help in dating his find, but just above the fracture line of the rocks, he has found the evidence he needs.
Here, a bush was burned by a prehistoric wildfire, and that remnant of carbon is why you see this black stain on the side of the trench wall.
The key to unlocking the age of the rocks is carbon-14, known as radiocarbon. Its molecular structure means that carbon-14 is a more unstable isotope than other forms of carbon. It's absorbed by growing plants, then radioactively decays at a known rate after the plant dies. So measuring carbon-14 in vegetation burned in a wildfire reveals how long ago those plants died and dates the rock in which the carbon is found.
And through this, we can reconstruct the evidence of the past earthquakes.
Radiocarbon dating has proved that earthquakes have been happening along the line of the San Andreas for thousands of years. The particular small earthquake investigated by Hudnut, for example, is around 3,500 years old. It happened at a time when the last woolly mammoths were dying out in North America. investigation moves to an even more remote desert spot, the Carrizo Plain, 160 miles north of Los Angeles. Here lies a dried-up riverbed, which takes an unusual course. Coming down off the hills, the creek bed takes a sudden, sharp turn to its right. A few hundred feet later, it makes an equally odd 90-degree turn to the left. The creek crossed the line of the San Andreas Fault, but early geologists were mystified. Why did it bend in this way? The scientific pioneers were limited to studies on the ground. Nowadays, Hudnut has an advantage. He can take to the air.
The San Andreas Fault, where it cuts through the Carrizo Plain, it almost looks like a scar, and it was caused by repeated earthquakes in the past.
Along the long line of hills marking the course of the San Andreas, Hudnut spots the puzzling bends that he's seeking.
Uh-oh. If we could swoop along the fault through here, that would be awesome. Oh, there's a great angle. See that right angle offset channel with the elbow in it right there? That's a classic one right there.
Hudnut's aerial view of the creek bed shows that the river once flowed straight on across the fault. But little by little, a series of earthquakes along the San Andreas dragged the creek away from its original course. Recreating how the land had moved showed Hudnut that the two parts of the creek had traveled more than 300 feet apart.
So if you imagine the North American plate is fixed and the Pacific plate is moving to the northwest, the Wallace Creek site records that offset because the channel was straight across the fault, but it's been offset through time.
Earlier investigators had already radiocarbon dated the land on each side of the fault here, revealing that it took 3,000 years to change the creek's position. So, knowing the distance and the time it took to do it, lets Hudnut calculate the average speed with which the two land masses are moving past each other. 300 feet in 3,000 years. 1 foot per decade. Just over an inch a year. But this was never a steady, sliding, 1 inch a year movement. The reality was a series of sudden, small jumps whenever tension built up enough between the two moving plates to overcome friction between the rocks and rip the land apart with an earthquake. It's an important moment for the investigation. Knowing how fast the land is moving not only reveals the stress that's building up, but also the risk of an earthquake. The San Andreas Fault is giving up its secrets. Clues from a long dried up pond reveal the site of ancient earthquakes. Carbon from a prehistoric fire provides the dates. And bends in a riverbed prove how fast the plates are moving along the San Andreas. But now the investigation has a new mystery to solve. If the land along the San Andreas is moving 1 inch every year, causing earthquakes, then why has one small town along the fault line never had any? The investigation has discovered how fast the land is stretching and straining along each side of the San Andreas Fault, which should help establish when that ever-increasing stress will snap the land apart in the next major earthquake. But there's a problem. One part of the fault line just doesn't fit the pattern. The small town of Hollister is unique along the San Andreas Fault system. It's never had an earthquake, and the investigation is going to find out why. Hollister has a population of 37,000. And nothing here is quite the way it should be. There are plenty of clues suggesting that the land must be moving here. Sidewalks with cracks in it, curbstones way out of line, and walls that are bent out of shape.
Walking through Hollister, we can see anything that man has built that was laid out in a straight line may have a jog in it. Every year it changes a little bit, and it's a progressive thing.
The clues add up to one clear conclusion. Even without any earthquakes, the Earth in this town, in the heart of the San Andreas system, still slides imperceptibly slowly and effortlessly along.
In one sense, the damage that you see here associated with the creeping is clearly sort of under control. But as a geologist, if you start playing that out for tens of thousands or hundreds of thousands or millions of years, the consequences of that become enormous.
For many years, the creeping ground that moved without earthquakes remained an unsolved mystery. But then, the investigation moved 100 miles south to another small community where the land also creeps along. The village of Parkfield has a population of just 37 people and a bridge which spans right across the San Andreas Fault. The bridge separates the Pacific Plate on one side from the North American Plate on the other. And the bridge railings have started to bend.
I'm right now on the Pacific Plate on the west side of the San Andreas Fault. And, you know, the San Andreas comes off the flank of that hill and right across that field, right under the bridge, and then right over by the corner of that building, or that fence post, and then on off to Middle Mountain.
The movement here around the bridge is strikingly similar to the slow creeping ground of Hollister. But there is one important difference here in Parkfield. Every couple of decades or so, this village does have earthquakes. They're just little tremors, but they're big enough to be recorded on earthquake monitoring seismographs. That's why the village proudly boasts of being the earthquake capital of the world. But it's perhaps more accurately called the earthquake study capital, because scientists are fascinated by the fact that earthquakes here follow a predictable pattern. Elsewhere, earthquakes always strike without warning. The toll of death and destruction made worse because nobody knew they were coming. So scientists are desperate for any clues that might help predict when an earthquake could happen. And here in Parkfield, the earthquakes happen with astonishing regularity, on average every couple of decades or so. Minor quakes happened here in 1857, 1881, 1901, 1922, 1934, and 1966. After the 66 earthquake, investigators set up a network of monitoring instruments to see if the fault gave any warning before the next earthquake arrived. They expected it sometime between 1988 and 1993, but it was late, and months of waiting stretched into years. But still, the scientists waited, until finally, in December 2004, the long-awaited earthquake arrived and was caught on film from a now slightly worn and damaged camera. The earthquake movie may not have seemed that impressive, but the instruments collected a mass of information. The data didn't, after all, help with earthquake prediction, but it did pinpoint where the earthquake started underground, which told investigators where to look next. Deep down under the Parkfield countryside. starting slightly to one side of the fault. The aim was to angle in and stab into the very heart of the San Andreas. After 3 years of drilling, long cores of rock were extracted from the exact spot where the earthquake occurred. This was the first time that team leader geologist Mark Zobak had ever seen rocks from the center of the San Andreas.
What we're looking at here are cores from the active San Andreas fault from a depth of about 2 miles. So for the earth science community, these are like moon rocks. As we were trying to exhume these cores, we had a great deal of drilling difficulty. The San Andreas fault was literally fighting back. After 9 weeks of attempting to recover the cores, in the middle of a huge lightning storm, almost a scene directly out of Hollywood, with the thunder and lightning, these cores came to the surface. And so it was a tremendous feeling of satisfaction. The lightning and thunder just made it that much more dramatic. And we're all wearing gloves. We didn't want any oil from our fingers to affect the core. And the rule was that you touch the core as little as possible, obviously.
I'm not gonna wait for you guys. Oh, look at this beautiful rock.
The reality was we couldn't help ourselves, and it was just such a remarkable thing to be actually looking at the San Andreas fault for the very first time. Then we all got to touch it a little bit.
Buried within the rock cores, they found a vital clue about the way that land slips along the San Andreas. They found serpentinite.
Serpentinite is an unusual rock type. It was originally formed at the base of the ocean crust and exhumed up onto the continent. But the reason that serpentinite is so interesting is that serpentinite is very easily altered to talc. It allows the rock to slide at very low force levels. Talcum powder is very slippery.
Talc's crystalline structure of soft, sliding, flat plates makes it one of the slipperiest rocks known to science.
So talc could well be a key mineral in deciding how the fault is actually working in Central California. We see that the secret of the slipping San Andreas fault is actually the rocks themselves.
The talc explains the tiny earthquakes of Parkfield. Nobody's yet drilled to investigate the rocks at Hollister, but scientists suspect the talc is present there too. Cracks in the walls show the land creeps in Hollister. And a bend in the bridge reveals the same creeping ground in a nearby town. Rock cores extracted from the fault contain serpentinite, leading investigators to the softest and slipperiest mineral, talc, which lubricates some parts of the fault. The investigation is having success, but one crucial question remains to be answered. What will the San Andreas fault do next? The investigation into the San Andreas fault is trying to predict when and where its next major earthquake will strike. So far, the only certain prediction is the far distant future of the San Andreas. Look 20 million years ahead. If the plate movements continue to follow their pattern, Los Angeles will end up becoming a suburb of San Francisco. But predictions on a shorter time scale are more difficult.
If you were to ask the question, can we predict earthquakes? My answer would be no, because I know what your question really meant is, can we predict that an earthquake is going to occur on a certain fault at a certain time that we can specify in the future? And we cannot do that. But there are many things we can predict. We can predict which faults are likely to produce the big earthquakes. We can predict how big the earthquakes are likely to be. And we can even predict the probability of the earthquake occurrence over some period of several decades.
Predictions are most crucial where the San Andreas runs to the south of LA. Here in the Coachella Valley Desert, geological evidence of earthquakes stretches back 1,500 years and more. And they follow a regular pattern. Major earthquakes strike here with monotonous regularity every 200 years. But the latest one is long overdue. There hasn't been an earthquake here for more than 300 years. That's a concern, because parts of the San Andreas fault system run straight from here towards the city of Los Angeles. The faults will transmit earthquake shocks in a straight line towards California's biggest city. Geologist Yuri Fialko regularly monitors how the ground moves on either side of the fault line. He lines up his GPS equipment precisely over a series of metal pegs fixed into the ground.
This information is crucial for estimating how fast the fault slips at depths and what is the rate of accumulation of strain in the crust. In other words, how close the crust is brought to failure by slip of the fault at depths.
The repeated ultra-precise measurements reveal that land here, on the surface, hardly moves at all. This is a problem, because deep underground, the stresses and strains are still building up.
The fault is moving at depths at a fairly high speed, and this deformation is growing and growing and growing with time.
Miles underground, the deep fault is moving at more than an inch a year, which tells Fialko that in the centuries since the last quake, the surface should have shifted 300 inches, 25 feet or more. But it hasn't. So sooner or later, something's gotta give. And Fialko knows what that something will be. The rocks themselves.
And one example is this type of rock, which is called granite, or this is in fact the rock out of which most of the Earth's crust is made.
A microscope reveals the crystalline structure of the granite. The crystals make the rocks tough, but they have a hidden weakness. The bonds between them may suddenly crack under stress.
Basically, once this material solidifies, it is able to crack and be sheared on the fault surface. And the brittle behavior of these rocks is what lies behind the physics of earthquakes.
Granite rocks underlie all of the San Andreas fault, but right here, the rock's under greater stress than anywhere else because it's so many centuries since a major quake occurred.
And now we're over the 300-year limit, and so it means that the amount of strain that has been accumulated on the fault at this point is very close to the maximum strain that this fault has ever seen through its geologic record. And this is a fault that is capable of generating great destructive earthquakes.
Fialko believes the coming quake could be the big one that people have been talking about for years. And the effects could be horrific because of the population density of Southern California. When the last huge quake occurred 300 years ago, Los Angeles was just a tiny Spanish mission community with fewer than 100 people. Now it's America's second largest city, with almost 11 million people living in the earthquake-vulnerable metropolitan area.
People who live in California probably experience a small or moderate-sized earthquake every year. A few things moving in your house, but it's really actually kind of fun. There is no major destruction. People just go on with their life. Much bigger events, on the other hand, are quite a bit different story.
With the threat to Los Angeles becoming ever clearer, the investigation is nearing its conclusion. Data from repeated GPS measurements in the desert reveal evidence that stress is building up, while examination of the rocks of the crust show they may not take the strain for much longer. All the evidence points towards a potentially huge earthquake building up in Southern California. And new experiments suggest the coming quake could be far worse than anyone had ever imagined. There is new urgency in the investigation into the San Andreas Fault, as revealed by recent evidence compiled by 300 of America's most respected scientists. They warn that Los Angeles will be devastated if a major quake strikes along the southern section of the fault line. While there hasn't been a major quake for hundreds of years, even small ones can still be deadly. Like the Northridge earthquake, which struck this LA suburb in 1994. Rupturing along an offshoot of the main San Andreas Fault, the quake was only a magnitude 6.7, considered moderate on the scale of earthquake measurement. But it still killed 72 people and injured 12,000 more. And new evidence suggests Mother Nature might have a lot more in store for Los Angeles. Scientists have long known that earthquakes generate several distinct sets of waves. They travel at different speeds, each spreading damage and destruction out from the epicenter. Modern city buildings in earthquake-prone areas like California are engineered to cope with such waves. Now, new research by geophysicist Professor Aris Razakis suggests that the San Andreas may offer a new and even more deadly threat. Razakis researches how earthquakes rupture along straight-line faults, just like the San Andreas, where it approaches Los Angeles. He creates his own mini-earthquakes, representing the San Andreas Fault by a hairline crack in a thick, transparent block. This special material shows up internal stress lines when it's lit by a laser. And the earthquake is triggered by a tiny explosion.
3, 2, 1, 0. The load has dropped. And the explosion was big enough that we even have a crack.
An ultra-high-speed camera capturing 10 million frames a second reveals a startling and newly discovered phenomenon. This frozen picture reveals stress lines speeding along the mini San Andreas in the milliseconds after the explosion. The cone to the left of this frame is a previously unrecognized type of shockwave racing along the rupture line from the earthquake's center. On a microscopic scale, it looks and moves exactly like the sonic boom produced when a supersonic aircraft such as Concorde breaks the sound barrier.
Because we also see map cones, lines that are emitted from the rupture tips as from the tips of moving airplanes.
And just like a sonic boom, it can be dangerous.
In the same sense that we hear the sonic boom from the Concorde, you're going to feel the sonic boom from the rupture.
The danger comes because many high-rises just aren't built to cope with extra stress from this newly discovered type of shockwave.
So if you are an old building, for example, you'll take one wave, you will accumulate some damage, and very soon after that, you will get very strong ground shaking because of other types of waves coming also.
The high-speed ruptures that Razakis calls super shear happen where faults run in a straight line, which might help explain a 100-year-old mystery surrounding the Great San Francisco quake, the natural disaster which launched the entire San Andreas investigation. The overwhelming damage in San Francisco has long seemed surprisingly out of proportion to the 7.8 magnitude of the quake. And there's a particularly straight section of the San Andreas approaching San Francisco. So many scientists now believe that the damage was greater than expected because the 1906 quake had traveled at super shear speed. Of greater concern to modern emergency services is not what happened a century ago, but what could happen tomorrow. Because there is a similar straight section of faulted ground heading straight towards Los Angeles. And if a super shear earthquake develops on that line, then the consequences could be disastrous. All of the investigation's warnings about the San Andreas came together in the fall of 2008 with the biggest earthquake drill ever held in California.
If this earthquake would have happened in reality, there would have been buildings coming down. We know that there would be no water now in certain areas. So that's what this exercise is all about.
But what are the real chances of Los Angeles soon being hit by a massive earthquake? Frighteningly, the best scientific consensus now warns that there's a 99% chance of a major quake in Southern California within the next 30 years. To better understand the threat to LA, the geologists produced their study jointly with experts in charge of the city's disaster planning. And none of them doubt that the big quake is coming.
It really isn't even a question of if anymore. The shaking is going to be severe for 2 to 3 minutes. And then it's going to stop. And then you're going to have that moment of silence that often happens before you start hearing the car alarms and all those other sounds that you have in a disaster like this.
The study estimates that a major earthquake in the LA metro area would cause 2,000 deaths, 50,000 injuries, and $200 billion of damage.
You're going to have conflagrations developing. Tens of blocks will be on fire.
The water lines have ruptured. There is no water coming out of the fire hydrant.
That's the kind of nightmare scenario that we're looking at.
This specter of disaster to California's people and cities motivates the search to unravel the secrets of the San Andreas Fault. All the evidence is finally in. The damage reports from the 1906 disaster show the fault's 800-mile path. The different types of rock at Muscle Rock provide clues to how the fault was created 20 million years ago. The riverbeds prove how fast the land is moving. The mineral talc explains why some parts slip without major quakes. The brittle granite rocks reveal a threat to Los Angeles. And recent lab experiments uncover new and more dangerous earthquake shock waves. But one goal has eluded the rock detectives who study the greatest fault line on Earth. When will the sleeping San Andreas come to life once again? It could be any time. The only certainty is that nothing is certain in the ever-evolving story of how the Earth was made. Earth, a 4.5 billion-year-old planet, still evolving. As continents shift and clash, volcanoes erupt, and glaciers grow and recede. The Earth's crust is carved in numerous and fascinating ways, leaving a trail of geological mysteries behind. In this episode, the Marianas Trench, the deepest point on Earth, is explored. Its sheer walls cut 7 miles into the Pacific Ocean. The mystery of what created this deep, dark chasm takes science detectives on some of the most dangerous dives ever attempted. Deep into the abyss. Scouring the ocean floor, scientists uncover a strange undersea world of fiery mountains, bizarre mud volcanoes, and the largest geological structure on Earth. Discoveries from this unique underwater world will revolutionize our understanding of the powerful forces that shape not just the trench, but the Earth itself. Hidden deep beneath the waves of the Western Pacific lies the Marianas Trench, the deepest point of all the oceans. The first step on the journey of what created this mysterious scar in the Earth's crust and how it continues to mold the planet takes us back to 1872, when a British research vessel, HMS Challenger, set out on the first ever mission to map the ocean floor.
Throughout most of recorded history, men have just assumed that beyond a certain level the sea was pretty flat, pretty dead, fairly lifeless. They weren't expecting to find anything very interesting.
For 4 years, the Challenger crisscrossed the oceans, covering 70,000 miles, a third of the distance to the moon. The crew plumbed the depths every 140 miles, using a total of 249 miles of rope and hundreds of pounds of lead weight. It was tedious, backbreaking work, but at the time it was the only way to measure the depth of the ocean floor. When they got to the Western Pacific, 200 miles off the island of Guam, the crew routinely lowered the rope for a measurement. But the weight kept on dropping and dropping.
It's a big surprise. Nobody thought the ocean was this deep. So all of a sudden we've got scientists saying, why is that?
Eventually, the weight struck the bottom at 4,475 fathoms, nearly 5 miles beneath the ocean's surface.
The scientists will be going, wow, we found something, and what does it mean? Is it a little hole? Is it a big hole? What kind of feature is it down there? There's a whole lot of questions you get when you find this one spectacular reading.
The Challenger expedition marked the birth of modern oceanography and provided the first crude map of the ocean floor. It showed how the ocean floor gently slopes away from the land and then plummets thousands of feet into vast flat plains. But the Western Pacific is different. It drops off again into the 5-mile deep hole, a hole that blew right out of the water the long-held belief that the sea floor was flat and featureless. And it spawned a mystery, because nobody could understand how this strange underwater feature came about. It would be 75 years before any answers emerged. It took a revolutionary new technology, sonar, to push the investigation forward to the next crucial stage. Sonar was first developed in the early 1900s and then perfected during the 1940s to detect submarines lurking in the deep. The system works by pumping sound waves through the water. The waves bounce off solid objects and are reflected back to a detector. By measuring the time it takes for the sound waves to bounce back, scientists realized they could build a remarkably accurate picture of the world beneath the waves.
The world's major navies spend a lot of time and effort developing submarine hunting technology. Then the hydrographers discover that you can use this to chart the bottom of the sea. And it's an awful lot cheaper and easier than using large numbers of sailors pulling on ropes.
In 1951, a British Navy research ship returned to the deep hole found by the Challenger expedition. But this time, they were armed with sophisticated new sonar equipment. And the results were amazing. Detailed sonar maps revealed that the deep hole in the Pacific Ocean floor isn't a hole at all, but part of a massive trench, 30 times deeper than the Empire State Building is high. It runs twice the length of California, 1,500 miles from the southeast of Guam to the northwest of the Mariana Islands.
people were probably astounded by what they were seeing, because clearly the ocean floor had enormous changes in relief, was very mountainous in some places, had great deeps in other places. To a geologist, this would be extremely exciting.
Even within the trench itself, there are remarkable variations. At its southern end lies the greatest surprise of all. The seafloor drops down another 2 miles to its lowest point, a staggering 7 miles beneath the waves. Scientists had discovered the deepest part of the oceans. Even today, it is the lowest known point on the planet. They named this part of the trench the Challenger Deep, in honor of the ship that discovered it.
To get a sense of just how deep trenches are, if we take the height of Mount Everest, we would still have about a mile of water above us before we get to the ocean's surface.
But how the Marianas Trench was formed remained a mystery. Investigators decided the best way to find the answer was to dive to the bottom of the trench, to see for themselves the lowest point on the planet, the Challenger Deep. But they faced a major problem. At the bottom of the trench, they would have to contend with pressure 1,000 times stronger than at the surface. That's the equivalent of being squeezed on all sides by the weight of 50 jumbo jets. To demonstrate the effects of such pressure, scientists use a dummy head.
Today what we're going to do is actually put one of these styrofoam wig heads in the pressure chamber and expose it to the pressure we would see in the Marianas Trench. That's about 16,000 psi.
A human skull would be crushed to a pulp, but the rubbery head will only have all the air squeezed out.
Wow, that's smaller. And here's what the original size was, just for comparison. Quite dramatic. Pretty stark difference between something that hasn't been 7 miles deep in the ocean and something that has. Glad I'm not going there. At the Mariana Trench, human life is impossible. We're not equipped to resist those kinds of pressures. And so it's necessary to protect humans from that type of an environment.
The challenge to engineers was how to accomplish this. In 1953, Swiss scientist Auguste Piccard designed the Trieste, a pioneering vehicle that could withstand the crushing pressures. The submersible was dominated by a 50-foot-long hull, filled with light aviation gasoline and lead weights to control buoyancy. Slung underneath it was a tiny 6-foot spherical cabin with 5-inch thick steel walls. Finally, after 7 years of modifications and manned test dives no deeper than 3.5 miles, the Trieste was ready to attempt the 7 miles to the bottom of the trench. The commander of this perilous undertaking was U.S. Navy Lieutenant and deep-sea explorer Don Walsh.
I know the astronauts that go through this all the time. Why do you have to be there? Why can't we just put up a robot to do things? Got to be there because that's what we do.
Only a few officers and scientists knew about the risky mission, which was launched in January 1960 from the western Pacific island of Guam.
Guam, in those days, was kind of a backwater. It was just right for us because we were trying to do this project sort of out of sight because we weren't too sure it was going to work. The Navy just didn't want to be embarrassed by a failed science spectacular.
Accompanying Walsh was the son of the Trieste designer, engineer and oceanographer Jacques Piccard. The two men would spend the next 9 hours squeezed inside the cramped sphere.
And we had 20 cubic feet of space inside. That's about the same as a household refrigerator. And the temperature was almost that cold inside. It was a drama.
The Marianas Trench is one of the most remote, inhospitable places on Earth. In January 1960, two deep-sea explorers, Don Walsh and Jacques Piccard, plunged into its depths on board the submersible, the Trieste. At a speed of just 3 miles per hour, they began their slow descent into the twilight zone. By 3,000 feet, the darkness was total. The only illumination was from the Trieste's powerful lights.
The depths we were operating at, it was always black. The only thing that lit up the abyss was the bioluminescence from animals and plankton. Like fireflies that carry their own light sources with them.
Encased in their 5-inch thick steel sphere, Walsh and Piccard quickly passed their test dive record of 18,000 feet. Everything appeared to be going to plan. At the rear of the cabin, the crew were protected by a double layer of glass. But 2 hours into the dive, the outer pane cracked.
We had a great big bang. We didn't know what it was. We were about 20,000 feet. And we looked around and checked everything.
Every square inch of their tiny life-supporting capsule was fighting back 8 tons of pressure. With the outer pane broken, the only thing between the men and instant death was a single pane of glass.
If the inner window had cracked, we would have been instantly dead, maybe even before we knew it.
But incredibly, the inner pane remained watertight. Walsh and Piccard decided to continue the descent. After a tense, claustrophobic 4 hours and 48 minutes, they approached the bottom of the trench, only to be startled by movement on the sea floor.
Just before we landed, we saw a flatfish about a foot long, and that's a bottom-dwelling fish, so if you see one, there are others.
Nobody expected to see life at these crushing depths, but it meant the explorers had reached their goal. The very bottom of the Marianas Trench. The depth gauge, with a reading of 35,800 feet, nearly 7 miles below the surface, confirmed the sonar findings. Squeezed inside their bubble of breathable air, the two explorers were closer to the Earth's center than man had ever been.
We took a self-portrait. That's the picture that you see. So we're going to do it, and we did it.
But there was work to be done. Walsh and Piccard wanted to make detailed observations of the enormous trench. Unfortunately, the Trieste stirred up a cloud of fine, powdery sediment from the sea floor that obscured their view.
It's like being in a bowl of milk at that point. So, realizing we're not going to see anything, we decided to go on back up to the surface.
Off the island of Guam and Trieste, surfaces after a descent into the Marianas Trench.
After 9 grueling hours underwater, Walsh and Piccard returned to the surface on January 23, 1960, and officially entered the record books for the deepest dive of all time. To this day, their extraordinary feat has never been repeated. The mission was a success, but the mystery remained. Geologists still didn't understand what could have formed the immense trench. And if they couldn't find the answer inside the trench, they would have to look elsewhere. Perhaps there was something somewhere on the ocean floor that might explain the trench's origins. Throughout Throughout the 50s and 60s, a team of geologists led by Princeton's Harry Hess compiled sonar data from all of the world's oceans. It was as though they had pulled out a giant plug to drain away all the water and expose the ocean floor. Their maps revealed that the Marianas Trench is just a tiny fraction of a network of enormous underwater canyons stretching right around the planet. But that wasn't all. Running parallel to the trench, on the other side of the Pacific, the map showed a giant underwater mountain range, the East Pacific Ridge. And this too is part of a global network, a 40,000-mile-long chain of mountain ranges that ring the globe like the seams of a baseball to make the largest geological feature on Earth. It was a major development in the investigation, one that scientists hoped might explain the trench's formation. The next step was clear. Investigators needed to understand whether there was a connection between the trench and the East Pacific Ridge. The breakthrough came from the unlikeliest of sources. During the Cold War, the U.S. built a vast network of underground seismometers to pick up atomic bomb testing around the world. Inadvertently, the seismometers also detected naturally occurring earthquakes. When geologists plotted these on a map, a pattern emerged. The earthquakes were clustered along the ocean's ridges and trenches. It was a discovery that transformed our understanding of the Earth. Geologists realized the friction that causes earthquakes comes from movements that must be occurring deep beneath the ridges and trenches.
With this great investment in seismology, it became possible to locate very precisely where earthquakes had occurred. And it was these things, the precise location, the depth, and the motion, that really gave the outlines of plate tectonics.
It was the birth of an extraordinary new theory. The solid layer of rock, the crust on which the land and ocean sits, is broken up into a series of vast slabs that geologists call tectonic plates. It's these plates that are moving, grinding past each other, and triggering earthquakes. The underwater ridges and trenches sit on the boundaries between tectonic plates. The East Pacific Ridge and the Marianas Trench lie on opposite edges of the Pacific Plate. The journey to discover what formed the Marianas Trench is accumulating additional evidence. The Trieste dived to the bottom of the trench and confirmed that it is the deepest point on the planet. Sonar maps then revealed the East Pacific Ocean ridge running parallel to the trench. To solve the mystery of the Marianas Trench, investigators needed to find out exactly what was happening at the East Pacific Ridge, and that meant exploring these vast mountains, 8,000 feet underwater. The pieces of the Marianas Trench puzzle are falling into place with the knowledge that it lies on the western edge of the Pacific tectonic plate. On the opposite side of the plate lies the East Pacific Ocean Ridge, part of an enormous chain of underwater mountain ranges that ring the globe to create the largest geological feature on Earth. Scientists had a hunch that this colossal ridge might help explain how the trench was formed. And they found a major clue halfway around the globe, where the ridge passed beneath the middle of the Atlantic Ocean. During the Cold War, the U.S. Navy developed a new technique to spot Soviet submarines. They scanned the seas with a tool called MAD, a magnetic anomaly detector, which could pinpoint steel hulls lurking in the deep. But but they stumbled across something else. Running parallel on either side of the ridge, they found strange stripes of magnetic rocks, alternating positive and negative away from the ridge's peak.
Here's the mid-Atlantic ridge coming down through here. Almost perfectly symmetric on either side of that are these white and black stripes. These have often been called zebra stripes.
Geologists know that the Earth is like a giant magnet with a north and a south pole. But the magnetic poles aren't fixed. Every 300,000 years or so, the magnetic field suddenly flips 180 degrees. When the field flips, a compass that was previously pointing north will swing to the south.
This reversing of the Earth's magnetic field is a very interesting and exciting but very puzzling phenomenon for geophysicists to explain.
Scientists think this reversal explains the stripes either side of the ocean ridge. In the 1960s, geologists discovered that molten volcanic rock, known as magma, swelled up from deep underground to create the ridges in the Atlantic and Pacific. As magma wells up between the tectonic plates, it pushes the seafloor up and forms the colossal mid-ocean ridge thousands of feet high. When the rock is hot and molten, its magnetic minerals line up with the north-south direction of the Earth's magnetic field. As the magma cools, the minerals are locked in position. These rocks act as a permanent record of the magnetic pole's location when the rocks were formed. As more and more magma is forced up, the old crust is pushed away from the ridge and records the reversals in the Earth's magnetic polarity.
If you have reversals of magnetic polarity, then the seafloor acts sort of like a tape recorder and records these changes in magnetization. Then the pattern of magnetic stripes allows people to calculate the speed at which the plates are moving apart.
The zebra stripes are proof that over time, the seafloor in both the Atlantic and the Pacific is spreading away from the ridges at a rate of more than 2 inches a year. But geologists needed proof that magma created the ridge. If red-hot molten rock is forming the enormous mountain range in the Pacific, the surrounding water should be warm. In 1977, a team of scientists set out to discover whether this warm water really existed. Dudley Foster was the pilot for these historic dives.
It's been an exciting occupation because you're on the cutting edge of science. New discoveries all the time. Every cruise, there's a new group of scientists with new scientific objectives. It was the exploration and the discovery. And that's really what puts the thrill in the job.
For weeks, the crew scanned the undersea mountains without success. And then they hit the jackpot. A bizarre pillar of rock, spewing hot, toxic gas.
And we saw the water sort of shimmering, sort of like bubbling in a glass teapot or something. We stuck the temperature probe in there and measured 38, 39 degrees Fahrenheit, which was really amazing because the ocean's a huge heat sink. So to see something warm like that was kind of startling.
In these pillars of rock, the expedition had found the heat from the magma surging up from deep inside the Earth. It wasn't warming the water evenly along the ridge. It was channeled up through strange hydrothermal vents.
When you make these discoveries, you don't know how significant they are. The true significance of them maybe takes several years to appreciate. And this was one of those times.
For the investigation into the Marianas Trench, These vents are a decisive piece of evidence. They confirm that magma is continually creating new crust at the Pacific Ocean ridge. And magnetic zebra stripes prove that old crust is pushed away from the ridge towards the other side of the Pacific plate, towards the Marianas Trench. But this presents scientists with a puzzle. If new crust is being created at the ocean ridge and the Earth isn't expanding, then the old crust must be disappearing somewhere else.
The reason that there's not getting bigger with seafloor spreading is because the same amount of seafloor is being destroyed in the Pacific.
Something in the Pacific Ocean is devouring the seafloor, and all the evidence points to the Marianas Trench. In the hunt to discover what formed the Marianas Trench, scientists now know crust created at the ocean ridge is being devoured somewhere and by something in the Pacific Ocean. They suspect the Marianas Trench is involved. But the proof would come not from the trench, but from these. The Mariana Islands, a chain of volcanoes that break through the ocean's surface 200 miles west of the trench. Scientists noticed the island chain mirrors the trench's exact shape. This led them to think the trench was responsible for the island's creation.
If you see pictures of the Marianas Trench, it's curved, and the line of volcanoes that it generates is curved exactly parallel to it.
Geologists believe that the trench formed the volcanoes via a process called subduction. Subduction occurs where two tectonic plates collide. As they grind past each other, the heavier plate is pushed beneath the lighter plate. The descending plate is forced down into the Earth's intensely hot interior called the mantle. It takes with it water and sediment built up over millions of years.
Volcanoes form above subduction zones not because the Earth is hotter there, but because this is where we're taking the water that once was in the ocean. It's taken into the mantle and gets sweated out, causes the mantle to melt, and this magma is what then rises and erupts explosively out these volcanoes.
The water in the sediment forces magma to swirl up and push through the plate above. And when it breaks the surface, it creates volcanoes, like the volcanoes that form the Mariana Islands. It was subduction that formed the islands west of the trench and gave investigators the breakthrough they'd been looking for. Because here at last was a process powerful enough to create the Marianas Trench. As the descending plate dives down, it digs into the mantle. Here, the colliding plates form a trench, a giant crease in the ocean floor. It seemed that scientists had finally explained how the trench was formed. There was just one problem. A very large problem. Around the world, subduction zones cause violent earthquakes and catastrophic tsunamis.
We know subduction is happening because of the active earthquakes, and these are the most devastating earthquakes. This is the earthquake that generated the tsunami in Sumatra. Also, the other very large earthquakes in Alaska and Chile.
But the Marianas Trench, the deepest subduction zone in the world, hasn't caused a devastating earthquake since records began in the 17th century. Investigators needed to know why.
That's a $60,000 question.
They hoped the trench's shallower western edge might provide the answer. Here they found an intriguing chain of underwater hills 2 miles below the surface of the sea. investigators drilled down into the hills and collected core samples. And when the scientists analyzed the samples, they discovered the hills were actually volcanoes. And they spewed out not lava, but mud. The fine powdery mud is made up of a soft type of rock that has been ground up in the subduction zone. It seemed this soft rock might explain why there have been no major earthquakes at the Marianas Trench.
Everybody has a sense of what a volcano is, but not all volcanoes erupt igneous rocks. There's some volcanoes that erupt mud, and a certain kind of unusual kind of mud in the Marianas is made out of serpentine. And serpentine is a very weak rock, and it can be scratched with a knife or something like that.
Investigators realized the grinding plates crush the soft rock to form a lubricating mud that prevents large earthquakes. Then the mud bubbles up to the ocean floor, where it forms the strange mud volcanoes found along the trench's western edge.
Other parts of the world, like the Andes or maybe Indonesia, you've got two plates that are grinding together, and one of the plates is quite strong. And it takes a big earthquake to rupture that plate interface. But if these rocks are weak, like they are in the Marianas, where you've got these serpentinites, those are very weak, and it doesn't take much energy at all to get the two plates to glide one past the other.
At last, geologists had discovered what created the Marianas Trench. 50 million years ago, the Pacific Plate slipped under the edge of the Philippine Plate. As it bent and dived into the Earth's mantle, it formed the colossal Marianas Trench. And the plate is still moving. Like a giant conveyor belt, the Earth's crust travels slowly across the Pacific Plate, from its birthplace in the East Pacific Ridge to its graveyard 10,000 miles away in the Marianas Trench. Today, the Pacific Plate's movement can be tracked in real time.
Confirmation has come from GPS technology, where we can actually put a transmitter on an island and come back year after year and actually follow it moving a few centimeters a year towards the trench.
It's devouring the crust at a rate of 3 inches a year, about as fast as a human fingernail grows. Every 4 million years, it swallows an area the size of the United States. By consuming the crust created at the Pacific Ocean Ridge, the ravenous Marianas Trench is the world's largest recycling plant. But there was one remaining and major piece of the puzzle to find. Scientists still didn't know why it is the deepest trench on Earth. They suspected the age of the seafloor at the bottom of the trench may provide the answer.
It turns out there's a really strong relationship between the age of the seafloor and its depth in the water.
In 1999, a team of deep sea drillers returned to the trench to collect core samples.
One great thing about drilling ocean crust is we actually got pieces of it. So we're holding in our hands here the material that's actually getting subducted at the Marianas Trench, and it turned out to be 170 million years old. So we can say with confidence that's the oldest ocean floor before it's getting swallowed up in the mantle at the trench.
But why is this piece of rock the oldest on the ocean floor?
The seafloor at the Marianas Trench is so old because it's been so long since it was born. So it was born in the equivalent of the Eastern Pacific today, and it's just been going on longer than any other place in the oceans before it's been subducted.
The Pacific Plate is the planet's largest tectonic plate, covering an area 11 times the size of the United States. When crust bubbled up at the ridge 170 million years ago, it was light and buoyant. But as it traveled 10,000 miles across the plate, it cooled and became compact and dense. Over millions of years, the dense crust got heavier and began to